Hello, everybody, and welcome to the July DeFi Security webinar. We have two fantastic speakers, and actually Nathan was the one who proposed the topic and the speakers. Before I go to the webinar today, let me remind you about the main DeFi Security Summit event, which is happening as part of Devconnect this year in Buenos Aires in November 20. We have already got the lecture hall from the Devconnect team. We got already quite a few great submissions, and we encourage more. We know that last year we were not able to get all the talks that were submitted, but this year we actually got parallel sessions, so we're going to accept more talks. We also, DeFi Security Summit is a very affordable event. The price is only $99, and we cover the event with sponsors. We have already great sponsors. I want to thank specifically Trail of Beat, which is sponsoring us for the fourth year. I want to thank Sigma Prime, which is sponsoring us for the third year. I want to thank Slido, sponsoring us for the third year, and Aave for the second years, and hopefully more to sponsor us. This is a marketing-free event. It's only to educate the community. There's one day 101, which is to teach people about security, and there is also the main talks where a lot of security teams said that is actually the most technical event in the crypto space. So we encourage more submission. We have a very nice committee, so please submit. So let me go to today's topic. We have the two of the most distinguished speakers in this space talking about zero knowledge. So the first speaker is Zac. I'll let you start.
Thank you very much. Thank you for that introduction. Hi, everybody. I am Zac. I am the CEO of Aztec Labs, and I'm a former particle physicist by training, now a cryptographer and an engineer. We've been doing this for 8 years. Our mission is to bring programmable privacy to Ethereum, and I'm here to talk a little bit about the Aztec network and to do a dive into what it is, how it works, our cryptography, and our protocol architecture. So without further ado, I will share my screen. Just give me a sec. Right, and I guess show. Okay, cool. Here we go. So this presentation is going to go through three major points. First of all, what is even privacy? What do I mean when I say privacy network? And then I want to go through the protocol architecture and our cryptographics tech stack, which makes it all possible. So the Aztec is a layer 2 smart contract. So we use Ethereum for consensus, and the goal is to present a Turing-complete smart contract capable transaction model, but critically different to existing ones out there. State can be encrypted, and instead of the state transition functions being handled by a sequencer or a Ethereum node or somebody in the public domain, what happens is users locally prove the correctness of their local private state transition functions, and then those zero knowledge proofs are sent to the network to be validated and aggregated. And what this means is that our network can have a state tree that is encrypted, and it enables end-to-end encrypted blockchain transactions. And this explodes the design space of what one can do with a smart contract, because with privacy, with encrypted data, you can now meaningfully put personal information on a blockchain network. You can put identity credentials on a blockchain network, which means now that blockchains can more meaningfully interact both with Web 2 and with the real world. Previously, the enforced transparency was a major bottleneck for this. And what I would say, hang on a minute, if you're seeing my screen, are people seeing the Zoom bar as well? Yeah, let's get rid of that. Okay, cool. So what do I mean by privacy? Because really there's multiple kinds of privacy in a smart contract, in a blockchain environment. You have user anonymity. So can you hide the identities of the transaction sender? but also do you have data privacy? So the data within a smart contract, for example, token balances, is that hidden? Can you hide what functions within a smart contract are being called? And can you actually hide the contract code itself? And so the goal of Aztec, and something that we have now achieved with our public testnet, is to encrypt all of these, so that it is possible to create fully private transactions where none of this information is revealed by a user making a transaction. How do I go? Next slide. And the way we achieve this, the contract model really is one where contracts are composed of two different classes of functions. You have private functions and public functions, where private functions will can call other private functions. They can call public functions, but the main thing is they can modify private states. So there's an encrypted state tree on the whose state root is learned by the network, and it's a UTXO-based model where, much like Bitcoin, you have individual state notes that are owned by entities, either owned by individuals typically, and that these notes can be created or they can be destroyed, but they cannot be modified. And one can use those to create more advanced abstractions, but it does differ fundamentally from Ethereum's account-based state model. And one can emit private encrypted events, and one can read historical public state. When I say historical, I mean you can read state from a version of the network that is not known to be current, because private functions are proven locally client-side, and so users will not necessarily have access to the latest state of the network. And in public functions, these operate much more like a traditional blockchain network, like Ethereum. They're executed by the network itself, not by individuals. Public functions and core public functions, they can modify an account-based public state model, and they can emit public events. And so you can have this hybridized public-private ecosystem within Aztec, where some state can be public, some state can be private. So to summarize a transaction on Aztec, a transaction is really a zero-knowledge proof of something we call the kernel circuit. So we borrow this nomenclature from the Zexi paper from 2015, but it's a very different type of architecture. The kernel circuit is one that is written by the Aztec protocol designers themselves, and it effectively it executes what part of what would normally be within something like the Geth software for Ethereum, where the circuit will validate that if I'm calling a smart contract, that the smart contract exists, it's been deployed, that the transaction correctly executes the contract logic via verifying a zero-knowledge proof. And then that zero-knowledge proof's public inputs will contain information about what that function called in that contract is doing. That will be interpreted by the kernel circuit according to a defined ABI. So it will read in nullifiers that represent destruction of UTXOs, new UTXO equivalents to be created, any messages to be emitted to L1, any new contracts that have been created, any event logs, and also any other function calls to be executed. And users will create these private proofs, and then one of the sequencer entities that produce blocks for Aztec will execute and prove the correctness of this proof. And so ultimately what's visible within Aztec is encrypted commitments and nullifiers, messages into and out of the L2 network that can be encrypted, may not be encrypted. It's up to the contract that emits those events, as well as public contracts that are deployed and the call stack of all the public functions that were executed. And so this is a rough anatomy of what an Aztec block is. Again, it's a rollup. The idea is, you take individual transactions, you combine them 2 by 2 into base rollup proofs, and then those base rollups get merged in a merge rollup, and then it will get aggregated into a root rollup. And this tree-based type structure just makes it much easier to prove these blocks in parallel using large numbers of physical devices. And so to try and summarize this all in terms of protocol architecture, we're processing a state transition function. So you have state hash of the old network, state hash of the new network. But unlike a traditional network, this is all done by zero-knowledge proofs, and unlike traditional ZK rollups, those our rollup proofs themselves verify proofs of individual transactions that are produced locally. And so the blocks can deploy contracts to L2, they can interact with deployed contracts, pay fees, and then the way that we handle communication to and from L1 from the Ethereum network is through inbox and outbox messages. And so there's no real fundamental understanding of say, an L1 token, for example, within Aztec. This is all handled through the message block abstraction, where one will have portal smart contracts on L1 that, when you deposit tokens into them, will send messages to a equivalent contract on L2. Effectively, what one is to deposit tokens into our L2, one escrows them within this special proxy contract on L1 that has a linked L2 contract. Yes, so, and to try and slightly visually lay some of this out. So the way this all works, L2 up to L1, is your L2 contract within the L2 network, will send and receive messages to the rollup contract. And our rollup contract has an inbox and an outbox contract to handle inbound and outbound messages, which will then communicate with portal contracts. So this is a fundamentally asynchronous way of communicating. It's not really possible with current tech, unless you have real-time proving. You can't really do synchronous composability between L2s, L1s, or between any blockchain network, because effectively, if the transaction, let's say we're doing an L2 to L1 flow, if the L1 component reverts in a synchronous composability model, then somehow the part of the contract that's executed on L2 also needs to revert. And so, yeah, our communication model is asynchronous. And yeah, like one of the things, this can be a slightly dull or less savory part of Web3, but I think that identity is going to be absolutely critical to making blockchain mainstream. And the fact that we're Turing complete, the fact that you can program contracts with arbitrary encrypted state, means that you can perform compliance. So the example here in this slide is like signature from a KYC provider, but that's pretty basic. That's pretty centralized. You can do other much more advanced things, like, for example, require and validate a proof of a passport that was issued by an NFC scanner. Or you can do basic Sybil protections, like you can prove that one has using ZK email or ZKTLS, like prove you have a Twitter account with over 100 followers to get some basic Sybil resistance into your protocol. Things like that. Yeah, and that's just the start of it. So how long have I got? I've got, we only got about a few more minutes. So I'll try to speed through this cryptography section. So the cryptography that we do is very, very custom. It's descended from the original Plonk paper that came out in 2019 with an enormous amount of iterations that have come from all over the design space of crypto, many different contributors at this point. But we use a Plonkish type system and client-side incrementally verifiable computation. So all of these functions, they compile to distinct circuits, and then they're composed recursively via an IBC scheme to make a single transaction proof. So the requirements for our cryptography is it needs to be low memory because we're doing client-side proving in a web browser. And for example, if you have an old phone, you've got about 1 GB of memory to work with. We need extraordinarily fast recursion or an equivalent like a folding scheme, because we're doing a very, very large number of these recursions client-side, both to compose multiple function calls, but also to reduce resource requirements, memory requirements. And the proof size needs to be small, and this is one that's often overlooked. But for a decentralized network like ours, to get the transaction on chain, one needs to send it to a peer-to-peer mempool. And where individual ASIC nodes are being run by individuals, so that the bandwidth of your node operators is going to be that of a broadband connection, and the bandwidth of the P2P network that they're constructing will be substantially less than that. And so if you have, for example, 1,000 TPS and your proofs are 100 kilobytes, then that's 100 megabytes a second of P2P network bandwidth required, which is not practical. Yeah, so having a small proof size is important. So our cryptography stack is we use something called HOC, which is a big derivation of Plonk. Proto-Galaxy, which is a descendant of Proto-Star, which is a folding scheme to fold these instances. We use something we call Goblin Plonk, which was developed by us to effectively eliminate the computationally challenging parts of folding schemes when using elliptic curve-based scheme systems. And we use a multilinear polynomial commitment scheme called Gemini. So Honk is a multilinear, as I said, Plonkish ZK snark with many, many changes. It uses a sum-check protocol as its polynomial IOP, as opposed to zero checking using quotients, as in the original paper. So this was first elucidated in a Plonk scenario using it from the Hyperplonk paper in 2020. It's pretty memory efficient. So if you have an execution trace, take every cell in your execution trace, roughly the number of bytes, multiply by 1.5, that's roughly-ish the memory. It can go lower. The multilinear PCS gives constant size covariance, which means extremely easy folding because you're just doing basic like linear exploiting basic linear homomorphisms from elliptic curves. And the polynomial algebra of the Plonker system supports a few gate types. So these are not really precompiles in a VM sense, but they're more just specific types of algebra that one can apply to a given row in an execution trace. So these are pretty small modules. You can do things like lookup tables, generalized set membership checks, which we use to create ROM and RAM abstractions and fast range checks, big integer arithmetic algebra. So you're doing big integer arithmetic, just having special polynomial relations that will do all the lim multiplications, and something which some custom gates that will evaluate one of the Poseidon 2 rounds. So we also use an execution trace width of 4, which is, by modern standards, very small. Most VMs have many thousands of columns, not 4. But this is partially because we want very small proof sizes for faster verification, faster folding, and for the fact that all proofs within the Aztec network need to be uniform, as in you need for simplicity, a uniform verifier. So Goblin Plonk is it's not a priming system, it's not an IBC scheme, it's an accelerator for IBC schemes, depending on that depend on elliptic curve arithmetic. I've got 1 minute. This might be a little bit hard to explain in 1 minute. So if you're folding an elliptic curve-based scheme, well, the good news is that your commitments are constant sized. So you don't have a huge amount of algebra to do to create linear combinations of these, but the algebra is going to be through non-native elliptic curves. So what we do is, instead of doing it within a snark circuit, we present as a claimed result of an elliptic curve operation. And then we store the inputs and the outputs of that operation in a transcript commitment. So this is just a column in the circuit that, when the circuit becomes a proof, will become a commitment. And per IBC step, these transcript commitments are accumulated into a single commitment. Again, like this is happening through basic elliptic curve algebra, which is non-native, but again, the non-native elliptic curve operation is required to accumulate transcripts, is deferred via Goblin Plonk into another transcript. A bit complicated. And then once one has one of these transcript commitments, we have a special snark circuit called a translator circuit, which uses a small number of non-native field operations, not group operations, field operations, 5 per group operation, to effectively transform the transcript commitment into one that's defined over a cycle curve. And then we use that cycle curve to prove the correctness of the transcript by effectively, at this point now, performing native elliptic curve arithmetic, because you're using the cycle curve. So all in all, it turns a non-native group operation into a native group operation and 5 non-native field operations. So it's extraordinarily fast, and it makes our recursion cost, client side, with limited resources, proven in the milliseconds. This is a diagram I don't have time to go through, so I'll just leave with the state of Aztec in 2025. Where are we today with our network, with our architecture, with everything? Well, the designs are all pretty much complete. The programming language that we use to write smart contracts, Noir, 1.0 has been released. We've launched a public testnet of Aztec where you can and people have built and deployed applications. And we launched our adversarial testnet today, where it's adversarial because anyone could be a sequencer, and sequencers control the upgrade flow. So we basically are inviting people in to pretend to be bad actors and try to break our testnet. And hopefully we will be launching our alpha on the Ethereum mainnet soon. And I wish I could give more details, but I'm afraid I'm being sworn to secrecy for the time being. But we're working very hard to progress into our audit phase and to finish our security audits, which is the last major step for us. Right, that's me. Thank you very much for listening. So I just noticed I had some questions, but no, I'm running out of time. There's a Polinomial IOP is a polynomial interactive oracle proof. So it's a way of taking a complicated arithmetic statement to find out a polynomial. So let's say you have like degree 1 million polynomials, a of x, b of x, c of x, and you want to prove that like a of x times b of x minus c of x equals 0. A polynomial IOP takes complicated polynomial algebra and it reduces it to algebra over individual points, generally through some kind of interactive protocol between a prover and a verifier that's transformed into a non-interactive protocol via a Schmidt heuristic. But techniques do vary.
Thank you very much, Zac. So we're going to have Zac again for the QA. Thank you very much for the inspiring talk. So the second talk is Eli, and after that, both of them will listen to your question. I have also some questions. So Eli, why don't you start and introduce yourself in the interest of time? Thank you. And I think Eli needs no introduction here, but still.
Hi, Eli Ben Sasson. I'm a co-founder and CEO at Starkware. Started my research on proofs, mostly publicly checkable proofs around 2001, started implementing them around 2008, got red pilled by giving a talk about them at Bitcoin in 2013. That was the first time someone realized that proofs can help not just with privacy, but actually with scaling of blockchains. And I was very fortunate to be the person realizing that, because that changed my life forever. And ever since, I sort of veered more into blockchain and proofs. The very first thing we did was the zero cash paper that then led to the Zcash, cryptocurrency. I was one of the founding scientists. That actually did not involve scale, that involved privacy. But I was always more interested in the scaling, and I was always more interested in stuff that doesn't rely on elliptic curves and quantum susceptible cryptography. So that led to Starks, and Starkware founded in 2018. What I want to do for this talk, and now Starkware is behind Starknet, and I have a bunch of proof systems out there, Stone and more recently Stu. Both are open source. There's also the Cairo programming language, which is the one that powers Starknet. And I think among its benefits are that it leads to very efficient Stark proof creation. But it's also a generally good language for smart contracts. I want to state very clearly that even though we're called a ZK rollup, we're not ZK. And privacy, that's stuff that Zac and Aztec are doing and excelling at it. Even though we're called ZK rollups, the systems we have right now do not offer ZK and don't focus on privacy. So I prefer to call this technology validity rollups, because we focus on validity proofs and using them to succinctly prove transactions. But I tried to fight that, those windmills of saying that you shouldn't call it ZK rollups, at least not our stuff. I mean, Aztec, you can call it a ZK rollup. But anyways, I think it's a lost battle. So it's called ZK rollups, but to emphasize, what I'm going to talk about is not related to privacy. It could, but it's not. Okay, so what I want to do, and this is a talk that I gave already several years ago. I want to talk, because we have a lot of big security experts. I just want to talk about, and I'll share my presentation. I want to just go over, the various. Do you see my screen?
Yes, yes.
So I want to just talk about the four attack surfaces that are unique to proof systems, and then discuss them, what we do to address them or acknowledge them in the context of Starks. Okay. So I want to say that there are, if you implemented a proof system that proves that Turing complete programs, right, generates proofs for them, then there are 4 unique areas. Of course, whenever you're dealing with Turing complete systems, and of course, Mooly is a much bigger expert on me, then you have the halting problem, which in layman's terms means you never, you cannot ever truly debug mathematically debug a complex enough framework. So in particular, whenever you're dealing with any framework that allows you to do any computation, then there's that whole area, but it is not unique to ZK proving, right? So I want to talk about the unique additional attack surfaces or risk surfaces for proof systems. And they lie into 4 and 1 auxiliary that is in the ZK setting, which, I gave you already an introduction saying we're not doing ZK right now, but I'll still mention it. So the first one is in the crypto primitives assumptions, right? What are the assumptions that you're making and what happens if one of them breaks, okay? So that's one area, that's one risk surface. We've seen this, for instance, for RSA a bunch of times over the years, where basically new factoring algorithms and heuristics led to increasing the moduli size for RSA to be considered safe, right? That's one assumption. Of course, SHA-1 or whatever, MD, I forgot which MD being attacked, and that's another kind of instance of these issues of the very basic crypto primitives that you're using. So this is true because all ZK systems, they are cryptographic system, and unfortunately, none of them can be built without some cryptographic assumptions. So you're going to have, that's one risk surface you have to be aware of. The second one is the protocol security analysis. So the way a ZK protocol works, and Starks are no different, is you basically use a number of cryptographic primitives, and then you also use, you build a protocol and you prove a bunch of stuff. Now, you either could have a bug in your protocol itself, or it could be that in the implementation of the protocol, maybe the white paper is fine, but actually the implementation leads to an issue. So this is related to the protocol, right? That's a second attack surface, right? A third one is arithmetization. So I'll get into details about that, but when you actually take your specific computation, you're going to need to, in some way, reduce it to a bunch of polynomial constraints. And then the question arises, especially if it's a complex system, the question arises, do the constraints adequately represent the computation you want? And here I think the analogy is, suppose you're going to build a chip, a CPU, right? Some collection of NAND gates that are connected to have some functionality. So you have to worry, like you have this high-level specification of what the chip will do, but then the question is, did you place the NAND gates and wire them together in a way that actually captures that correctly, or maybe there's some error, okay? So that's arithmetization in the case of proof systems. And then finally, there's the actual basically code of the system itself, in which you wrote, usually the arithmetization will lead to some, either DSL or high-level language. And then there's, of course, the question of the specific code, which now is a little bit different because it deals with a cryptographic system. And then the fifth attack surface, which is only in the ZK setting, is what happens about leakage. Like, ZK is about privacy and preventing certain things from being leaked via the proof, but maybe something else in the protocol will leak things that so maybe the protocol is fine, but you somehow by mistake leaked stuff. So now I just want to go over some of the ways these things manifest themselves when we construct our ZK Stark systems and what we do to address them, okay? So first of all, what are the crypto primitives or assumptions when you build a Stark system? So there are actually 2 modes in which you can instantiate the Stark. In the purest and simplest way, but one that is interactive, an interactive Stark, which basically works something like this. The prover sends a commitment, a Merkle tree commitment, and then gets some randomness, then sends another commitment, then gets more randomness, for a few times, and then finally gets more randomness, which specifies a bunch of queries to the various Merkle trees, and then the Merkle trees are open. Then some decision circuit is applied. Okay, so in an interactive Stark, we know to prove that all you need is some collision-resistant hash. It doesn't have to be a cryptographic hash function, just some collision-resistant hash. So it's a very, very mild assumption, and that is the only assumption that you need. Beyond that, everything is proven based on math. And by the way, when I say proven, I mean even if your adversary is computationally unbounded, can run a quantum computer, can run for time 2 to the power. No, sorry, I take that back. Sorry. If it has too much running time, then it actually can probably break your collision-resistant hash. So I take that back. But it certainly can be a quantum computer. That's fine. As long as you have something that is collision-resistant for the attacker, then you're fine. If you go to a non-interactive Stark, which means you basically use the fiat shamil, then you require more from your hash function. You basically are going to apply the fiat shamil, and you want your hash function to be something that you believe is a good, a good thing that you can treat it as a random oracle model. Now, the random oracle model, for those of you who know, is something that is actually impossible because, like, from a Kolmogorov complexity kind of approach, you can never have a succinct random oracle. But nevertheless, for better or worse, the world is very comfortable using the fiat shamir heuristic and treating things like SHA-2 or Ketchak or Blake as random oracles. But I'm saying that's if you want the non-interactive Stark, that's the kind of crypto assumption you have to work with. The nice thing is these assumptions are widely believed to hold also in a world where you have efficient quantum computers. So there's hope for using Starks, both interactive ones and non-interactive ones, even if tomorrow there's an efficient quantum computer. Okay. The second kind of let me just see this. This is just something that I took from a blog that I wrote a very long time ago. There, I can share the slides with Mooly. We can share with you and with Nathan, and he can share with you. There's a blog and a video where I discuss this. This is many years ago, right? This is already, I haven't updated it in the past, I don't know, 5 years, so it's not up to date. But basically, different proof systems, I'd say the big dividing line is ones that are require only symmetric cryptography as their assumptions, and they're plausibly quantum resistant. And this is some collection of things that were at the time 5 years ago. And then you have the stuff that is based on asymmetric cryptography, number theoretic assumptions, and those could be Shor's algorithm breaks a lot of them, I think, are pretty much all of the ones that I'm aware of. And you have a bunch of them. So that's like, there's some sort of dividing line between different, big families of proof systems out there. Okay. Second thing I want to say, again, in the context of Stark, is like, how much do you trust the protocol security, right? The actual protocol that was designed, is it okay? So here, usually what people do is they, refer to peer review, the test of time. In general, the more eyes look at it, the more times it's whatever quoted or referred to, and others look at it. That's better. So a lot of the core protocols of Stark have been, appeared in like leading conferences many years ago already by now, from 2018, 2013, 2015. So they're like roughly 10 years out there. In particular, one thing that the Ethereum Foundation asked us to do as part of the ETH Stark project that we did and started in around, I'd say, 2019 and finished it about a year later, I think. They wanted us to do a second mathematical audit. So we basically contracted 2 esteemed, independent professors, Professor Venkat Goswami and Professor Amnon Tashma, and basically gave them all of the core papers on which the Stark protocol was based and asked them to, scrutinize them, try to find bugs in the analysis. And that's the second thing that we did in that case. They filed a report. There was in one of the soundness proofs of the first Fry analysis, actually, Professor Tashma did point out a bug, but by the time that was discovered by him, there were already 2 or 3 better and more tight analyses of the same protocol. So now you can always, like, with all of these mathematical protocols, you have to ask yourself, am I confident enough that these things are sound? I know that by now, folks are starting to talk about using things like, Lean and, Coq and other automated theorem provers to try and give even more robust proofs to various protocols. I think it's a spectacular effort, and yeah, I hope that all cryptographic protocols get to that level. Anyways, I'm saying that is another kind of security surface that exists there. In that context, it's very interesting that recently there was a beautiful piece of research coming from Ron Rothblum, and I forgot who else, like it was a year ago, that showed a very, very nice result, something that says like this. If you take, there's a beautiful protocol for, for kind of Starks or things that rely only on symmetric cryptography, that's called the GKR protocol. Goes back to a protocol by, it's based on the sumcheck protocol, but then, sort of made or beefed up for general computation. And what the researchers found is that, okay, the protocol is okay. When, however, you use the fiat Shamir protocol with respect to it, then certain claims can be broken. And that was and they even have like the kind of claims that can be broken don't depend on, like, no matter which hash function you instantiate fiat Shamir with, you could still make a false claim. And that's a very interesting discovery. So, that's like one case of a protocol that, let me just clarify. The GKR, just like in point 1a above, there's an interactive version of the GKR protocol and a non-interactive. So the interactive version of the GKR protocol actually is one of those few cases where no cryptography is needed, no cryptographic assumptions is needed. However, it works only if you have a very large number of rounds of interaction. So that part is completely safe and there's no issue with the protocol. However, in many cases, the GKR protocol is then instantiated in an interactive setting, and then the attack was shown on that thing. So that's just an interesting case from recent times of this kind of attack surface on a protocol. The third kind is arithmetization. And just want to explain what arithmetization is. So arithmetization, you take usually a problem about computational integrity and convert it into a problem about some relation between a bunch of polynomials. And here's just some examples. So someone wants to prove to you that a string Z that is 256-bit long, Bob claims he knows a preimage of Z under SHA-2. Okay, that's a computational claim, right? It's something about the way SHA-2 works. So what is arithmetization? It reduces this problem or this claim to a claim about polynomials, right? The sort of the verifier produces 2 polynomials and some degree bound D. And now there's a new claim that the verifier is saying, Bob, you want to prove to me that you know that there exists some y such that SHA-2 of y equals Z. Instead of that, please present 4 polynomials, A, B, C, and D, all of them of degree utmost D, such that a certain relation exists. For instance, if you plug, you replace the various variables in Q with all kinds of polynomials, then you get some equality. So that's an instance of arithmetization. We started with a claim about computation. We ended with a claim about polynomials. And this is very efficient because it's very easy to test using randomness whether a claim about polynomials holds true. and I won't go into this. So arithmetization just means, who said that you did this reduction correctly? Like, what if, the polynomials Q and R are not really the right things for you to check in order to know that the preimage of Z is Y, right? That's the question that's the risk surface. So what did we do about it? The way we addressed it with our Stark systems is that we designed arithmetization essentially for a very lean virtual machine that's Turing complete, the Cairo virtual machine. It is so lean that it has something like 50 polynomial constraints, and many of them are very, very simple ones. And then what we did is we applied actually the lean automated proving system and showed that the specification of the virtual machine equals the set of polynomials. Arithmetization works. And by then, there have been a number of other white papers by Jeremy Avigad, Professor Jeremy Avigad, an expert on automated theorem proving from Carnegie Mellon, and a bunch of folks from our team, led by our CTO, Leo Goldberg, to discuss this. But I would say that maybe arithmetization, it could be the 3 and 4 are the parts that I think are most scary. And then 4 just means that you in the end you implement things like the verifier by code. In particular, when we run our layer 2, it's going to be code written in Solidity that verifies a Stark system. And then again, you could just have bugs there. So the way we approach that is we did a bunch of audits by crypto experts and others, and then a whole bunch of audits also for the recursive part of it by internal independent team. And I guess this thing that says soon, this was like 3 years ago. So by now we've done it. So just summing up, there are 4 unique attack surfaces to cryptographic proof systems. I described a little bit what we did in our case. There's a 5th one that is very interesting in the context of ZK leakage, but that's not something that we're dealing with. And with that, I end my presentation. Thank you very much.
Thank you very much. Thank you very much, Eli, for inspiring and talking to us about the potential risks. Maybe Zac will join too. Let's see.
Yep, I'm here.
Okay, so I see that so far no question. I start by one question. It's a bit generic. I'm sorry about it, but I think for both of you it will probably mean something. What are the biggest? I mean, you have been both leading this space, but what are the biggest mistake, or at least one big mistake, you can share along the route? I mean, Eli, you go and you went to the Ethereum and later on to BitNet, and Zac, in your approach here, is that something that you can have done? I mean, Zac, you did not yet launch, but you will soon launch. But I understand you cannot. If you could change something, what is the one thing you guys can change?
Well, that's a big question. Should I go first? What
Sure.
could I change? What mistakes have been made? I mean, it's I've been doing this for 8 years, and I mean, I've gone down a lot of blind alleys in that time. We're close to shipping the thing of like the Aztec network, which is something I've been wanting to build for about 7 years. And if I'd known how to do it, as in if I'd known the cryptography, if I'd known the technology, I could have got it done about 5 years in the past. But instead, I think I've probably spent, I don't know, roughly 2 years, working years, entirely on trying to solve snark recursion. Like the various random schemes I've come up with over the years, it's enormous amounts of time spent. And then following schemes turn up, and it's like, oh, okay, well that's solved then. But what other things? I think honestly, okay. So when I randomly bit. When I started Aztec, like the hardest part, I thought the hardest part was going to be like effectively inventing the required technology, doing the research, getting the papers out. And then once I'd done that, I realized actually, no, maybe I think the hardest part is probably actually productizing this, and like turning an idea of like a paper into actual software, into code, into products. And now later on, a few years later, I'm like, actually, no, that's not the hardest part. The hardest part is literally organization building. It's actually building a team of people around you that have the skills, the mission, the narrative, like the drive to execute on this. Because what we're trying to do is so much larger than what one person with one mind and two hands can achieve. And so I've had to learn a lot of lessons the hard way in that journey. Yeah, I can't think of anyone like there's so many I could come up with. But basically, yeah, like spending so much time researching blind alley snark recursion methods was a big waste of time in hindsight.
Okay, well, I'll let you answer, and then we have many questions from the audience. Let's try to answer them one by
Can
one.
you just repeat the question?
So the question is, what's the biggest mistake that you have done since you started Starkware? Maybe, I mean, you worked before on Snark, I guess, but what's the biggest, I mean, decision, or I don't know if the mistake could be a different one.
Yeah.
What maybe not the biggest, an interest.
Okay, first of all, I'm sure we made many big mistakes. The only issue like with mistakes is that it's very hard to say. I'll mention a few things where we had like huge debates, and I'm not sure we made the right decision. But the reason I'm not saying that it's a mistake is that I haven't seen the other route of it, right? So let me just mention a few things. Our first prover was over very large fields, and that was unnecessary. That stone, which led to something that's much slower. And now Stu, like over small fields, is much faster. And I remember that it pained me even back then. But so like if I had a time machine, maybe I would go back and insist on it more. But I'm not actually sure that it was a mistake because there were very good reasons at the time. Like it's simpler, and Ethereum, gives the same cost for verifying small numbers and large numbers. So like in some sense, if that's your metric, and it was the limiting metric for a very long time, it's sort of even more efficient to use like very large numbers. That's one example. The other like really large example that I really don't know is like, we went with the Cairo VM and led to a completely different stack, right? That is not EVM compatible. And right, like this really big question is, was that a wise choice or not a wise choice? And I don't know. Like the jury is still out in the following sense. Like I think we ended up with something. I know we ended up with something that is way more efficient and scalable for generating proofs. And I also strongly believe it's because it's like a second generation smart contract language. I think it's actually better as a smart contract language. However, certainly, in terms of like integration and, DevX and stuff like that, yeah, it's like a new language. But the jury is still out because I think that like if we have like one killer app and one use case that everyone wants, then this may solve for the second problem. People will come in and they'll say, oh, you know what? Actually, Cairo is a better language. And so I don't know, but those are like two very strong cases where I'm not sure if we made the right decision. Large fields from the start, and then Cairo as a dedicated VM. Yeah. I can start answering. I see there are like some.
Yes, do you want to? So do you want to answer? I think this is for both of you. What are the key issues by Fabio? What are the key use cases where Aztec is preferred over Snark and vice versa? Who wants to take it first?
I can take it first. I'll take the first two questions very quickly, and then so the first question is like, for me? I think the huge trade-off between something that is privacy focused and let's say scale focus is really about like privacy. Like if you really care about privacy, definitely you want to use Aztec and not Stark. But the trade-off, at least as best that I remember, is that you have to understand that you'll probably pay in UX mostly. Like the UX won't be as easy, the various integrations coming in and coming out and stuff like that won't be as smooth. So I think if you need privacy, or the more you need privacy, you must use Aztec. If you are somehow fine, like most crypto users show with their choices, and you want good UX, you want that. And I just have to answer the second question. Why would you rather hold most, if not all, blah, 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 on Starknet versus Aztec? So first of all, there's an assumption here that you're assuming that we each, that I'm not like, don't have a large bag of Aztec or not long. So, I'm not going to answer where my beliefs are. But I think there is something like generally, right? I think there is something a little bit emotional about like, projects you're somehow involved in. But you may be right that the rational choice for any sort of crypto person is to diversify, not just among Aztec and a bunch of other things. But not investment advice. I'm very, very supportive of Aztec. I think it's a great project, and I'm long Aztec. Again, not investment advice. I don't know what the token is going to do. I also like Starknet and STRK. Again, not investment advice. So, anyways, that's my answer.
Zac, do you want to take a
Yeah.
shot here?
I think when it comes to use cases, you kind of hit the nail on the head there. And obviously, I'm way too biased and too invested in Aztec. So I think, imagine if for either of us, if we withdrew a bunch of tokens and then put it into another project, it doesn't really, it's not a great sign. But one of the key advantages of Aztec is that if you as a founder get kidnapped by French bandits, and they demand your money at knife point, then you can give them 10% and claim it's all you have, and they won't know. They won't know.
Interesting.
That's a bit dark.
That's a good one. Yeah. Now there is another one, I guess, in Belgium. So the third question, I don't know. Can you use ZK proofs to verify that the contracts are signing from your hardware wallet is verified and not malicious? So who wants to take this?
Well, I think what does verified mean? Because if it is already signed by something, it's like verified means signed, then you just need digital signature. If you mean that someone has passed it through some code that checks it, and then you have a proof that is secure, yes, then definitely you can do that.
Okay, then there is a question actually by our audience. Actually, that's very important for people who are attending here. There are a lot of people who want to learn, I guess, Cairo, Noir, we are seeing. So actually tell us, yeah, so what actually is the biggest problem from actually interesting for me too. What are the biggest issue from assuming the infrastructure is right? I know you have both complex infrastructure, but what's the user level mistake and for security researchers who are looking to learn things, what's the background? Do you need to go and study PCP or things like this to be able to understand these things, or can you just read code and find bugs?
I can tackle this one. I can start with this one. So there's many layers of abstraction within networks like ours. So what layer do you want to specialize in, really? Because it's a struggle to do all of them. I don't think that a security expert at this late stage really needs to learn about cryptography from a fundamentals or first principles level. We've been if they need to know cryptography at all, because networks like Aztec, like Starkware, we have domain-specific languages, not Cairo, and so there's a huge amount of understanding those languages and their architectures is a great place to start, because I'm not entitled about the specifics of Cairo, but take Noir. What it does is it compiles into an intermediate representation called abstract circuit intermediate representation, which relatively directly translates into constraints. And so understanding the ASIR level quite deeply is sufficient to detect things like, for example, whether there are under-constrained bugs. That's the main class of bugs in circuits. It's you're performing a computation, you're improving that computation being performed, but the proof isn't complete. The checks aren't complete, and so some issues can leak in. There's also just basic protocol architecture, like a lot of standard blockchain security practices apply and transfer over. At this point, like the cryptography is buried so deep within abstraction layers that just understanding our programming language at a deep level and understanding our protocol architecture is like 90% of the battle.
Yeah, I'd say it's the same. We have a different programming language and intermediate representation, but it's the exact same answer. Almost all of the security folks working with us, and there are many of them, a lot of auditing firms and so on, they what they specialize in deal is with that. And for that, you don't need to know any of the cryptography. It's about either the intermediate representation or the high-level language. In our case, Cairo, and the intermediate one is called Sierra. And that's where everyone focuses on Of course, if you want, like you could like study the cryptography and look at the actual protocols, but for most security folks, that's not needed, and it's not what they want to do. And there's more business in the just, you know, auditing and checking security of the smart contracts, I think.
And is there something specific on the sort of the application level that you need to understand something about them? Or it's essentially you're implementing anything?
Maybe for privacy, I would say things like, well, leakage and like, assuming that the ZK is fine, so like whatever you, but there is this distinction between, you know, witness, which is the stuff that's supposed to be, you know, preserved, and the ZK preserves that. But like I could easily see cases where a programmer, you know, wouldn't be aware of this and then do something where stuff that, you know, passwords could somehow leak somewhere. So like this distinction is in the case of ZK. In the case of like Starknet, it's irrelevant because we're not offering privacy, and then it's just like you know, auditing Solidity codes or Move codes or whatever, Solana code, smart contracts.
Yeah, totally. You know, the book around like safe private smart contract development is yet to be written. And so there's likely going to be a lot of mistakes made along the way. Yeah, as you said, like because our protocol supports both public and private state, it's very easy to write a contract where, you know, everything's public. So just the fact that one is using Aztec does not make it private. The contracts have to be coded up correctly. That requires an enormous like the meta around doing that securely is still a work in progress. Yeah, I'm pretty sure we even have grants open. If you go to our website, go to our grants page, if you to help us with that.
By the way, I'm just thinking online here. I'm guessing that Zach and the team have already done such things. But if there could be some sort of, I don't know, like debugger or parser that, as it looks at, let's say, you know, a bunch of noir programs, would sort of just highlight, oh, look, here are things that are actually shielded, and here are things that, you know, you just like green and red, like this stuff is, you know, be aware that this will be known because whatever, it's exposed somewhere, like what things are actually being protected and what things might leak.
Yeah, that would be nice. That would be nice. I think it should be fairly, I mean, because we already have separations into public and private functions, it's fairly straightforward where like if stuff's turning up in a public function, it's not public. So I mean it's not private. So but yeah, like having visual descriptions, having actual debugger information.
But then when you compose them and like, you know, you have libraries and like you know, how do you track that and say, I mean, you know, it was private somewhere, but now by mistake was
So in programming language, people have information flow. Unfortunately,
reach out to our grants team. We'll pay. Anybody who wants to do that, we'll pay you.
Okay, so we have to wrap. Sorry about it. Thank you for your time. You can feel free to reach Eli and Zac on question. We're gonna publish the YouTube very soon. Thank you very much, Eli and Zac, for teaching us, and please submit papers to DeFi Security Summit. Thank you, everybody.
Likewise. Thank you so much.
Thank you.
Cheers, Eli.
Bye.
Cheers, Mooly. It's been great. Thank you.